S2.2.14, which is looking at formal charge. So here's sulfur dioxide as an example. We've got oxygen with 6 electrons in its outer shell, the other oxygen with 6 electrons in its outer shell, and sulfur with 6 electrons in its outer shell. One way of putting those together is for sulfur electrons to go across there. Oxygen normally forms a double bond, so we've got a double bond there. Oxygen's now got its full octet. We do the same on this side. Again, oxygen's got its full octet. Sulfur has got an expanded octet, and that's because it's in the third period, it's got available d orbitals. Here is what that looks like. Now, it's a trigonal planar structure because we've got a lone pair pushing down. This lone pair is pushing down on these bonding pairs. We'd expect this to be 120 because of the lone pair, because it's trigonal planar. Because of the lone pair, that's going to push it down even further, so we get a bond angle of 117. So that's one way of putting the Lewis diagram together. We've got another way of putting that together. What's happened here is this bonding pair here, the oxygen has pulled those electrons back onto itself here, making this a single bond, or the same could happen this side. So we've got one of 3 options, and it's not a case of which one is correct, it's more a case of which one is stable, because they're all going to be formed. We need to work out, using formal charge, which one is more stable. So the concept of formal charge is that the thinking behind it is we ignore the differences in electronegativity. We assume pure covalency in the bonds, i.e. the electrons are in the middle of the bond, not more towards the sulfur or more towards the oxygen. All we need to do is count the electrons that belong in inverted commas to each atom and compare that with the number of valence electrons when the atom is not bonded. And we get this equation here where formal charge equals the number of valence electrons in an unbonded atom when it's not bonded, take away the number of electrons that are assigned to the atom in any particular Lewis structure. That green box is the number of electrons, valence electrons, it's grouped from the periodic table. And here we assume that each atom has an equal share of a bonding pair. So this electron pair here, sulfur has one, oxygen has the other, that's all we're saying. And the atoms own their own lone pairs. This lone pair only belongs to sulfur. It's not got, oxygen doesn't have a hold on this, and neither does this oxygen. Let's have a look and see what that actually means in a specific example. So here's our equation again. The number of electrons assigned to an atom in a Lewis formula is equal to this. It's half the number of bonding pairs, electrons in bonding pairs. Of course it is, that makes sense because in any covalent bond, one atom has one electron and the other atom has the other electron. And the number of assigned electrons to that atom is also added to that is the number of electrons in lone pairs. So the number of electrons is half the number of bonding pairs plus the number of electrons in lone pairs. And we're going to have practice at using that if that doesn't make any sense. What we're after is a zero formal charge. That's the more stable, the more preferred structure. Let's have a look at SO2 again. So here are 2 different versions of SO2. Sulfur, it's got 4 bonding pairs, 1, 2, 3, 4, and 1 lone pair. There it is. The formal charge is therefore going to be the number of valence electrons. Sulfur has a valency of 6. So the formal charge is going to be 6. Take away the number of electrons in bonding pairs. This is the purple bit that we're working out here. The number of electrons in bonding pairs, which is, half the number of electrons in bonding pairs. So we've got 1, 2, 3, 4 bonding pairs. 8 electrons, half of 8 is that 4. And then we've got 2 electrons involved in this lone pair. So 6, take away the 4, add the 2, equals 0. So sulfur has a formal charge of 0. On our left oxygen, this one here, we've got 2 bonding pairs. So if we have half the number of electrons involved in the bonding pairs, 4 electrons, so there's 2 electrons in those bonding pairs. Oxygen has a valency of 6, take away the 2, and then we've got 4 electrons in the lone pairs, gives us a 0 value. Great, that's for the left-hand oxygen. And the right-hand oxygen you should be able to see is exactly the same. So overall we've got formal charge, formal charge, formal charge on S, the left-hand oxygen and the right-hand oxygen. Let's have a look at this one over here. Sulfur has now got 3 bonding pairs and 1 lone pair. 1, 2, 3 bonding pairs and 1 lone pair. So the formal charge equals 6, that doesn't change, sulfur is in group 6. Take away the number of electrons in bonding pairs divided by 2, so 6 divided by 2 is 3. Add the 2, the number of electrons in the lone pair is a formal charge of +1 on this sulfur. My left-hand oxygen has 1 bonding pair and 6 non-bonding pairs. 3 lone pairs, which is 6 electrons. So 6 from the periodic table, take away 1 of these electrons, plus 6 electrons equals a formal charge of -1. This oxygen here is exactly the same as this oxygen here, which is this one here. So we can say that again the formal charge is 0. What does that mean overall? Well, what it means is that when we've got these two structures, in here I've written in red the formal charge for each of these atoms as we worked out up here. And over here, again I've written the formal charge, and you can see that this one is correct. It's got 0 formal charge. This is the more preferred structure because of this.